Hi everyone. This is an introduction to what I consider to be the most important topic in statistics. Understand this topic and it unlocks an understanding to virtually the whole course, the whole introductory course. The topic we're going to talk about is sampling distributions. And what a sampling distribution is, some distribution, some histogram that's created from sampling from a population. And this is important to remember. It represents the results that can be expected if one samples from the population. Most introductory statistics is based on two sampling distributions. The sampling distribution of the sample mean, called the sampling distribution of the mean, and that's for quantitative data, and the sampling distribution of the sample proportion, or the sampling distribution of the proportion as it's called, and that's for qualitative nominal data. Using computer simulations, as we'll do here in a few minutes, we can actually build accurate models of sampling distributions, develop intuition about the results can be expected from these samples, and then make inferences, make guesses about the population based upon this intuition. The inferences will come later in the course. But for today, we're just going to learn what is a sampling distribution and how you can use it to find probabilities of certain things happening. Okay, so what I'm going to do is I'm going to go to another site. And this site is a simulation. And this black histogram here is a population, a normal population. You know, the smallest values are 0, the largest values are 32. The mean is about 16, so most of the values are here in 16, 14, 15, 16, somewhere in that area. So what I'm going to do is I'm going to collect a sample from this population. So here's a sample. We'll say our samples are size 5. It's okay. Animate it. Okay, 1, 2, 3, 4, 5. We take a sample of size 5. That's what these black values represent. And from those samples of size 5, we calculate a sample mean. That's this blue bar down here. Now, I could do this again. 1, 2, 3, 4, 5, 5 values, and we get another sample mean. Alright, now, I could do this lots and lots of times, if I could do it lots and lots of times, and that's what I'm going to do. I'm going to do it not just, say, one time, I'm going to do it 10,000 times. Okay, so what I just did is I collected 10,000 samples of size 5 from this population. For each one, I calculated the sample mean, then I plotted the sample mean down here in this histogram. Well, I can do it again, and again, and again, and again, and again. Notice that. So what I've done is I've got, you can see over here, about 120 samples, all of size 5. And I calculated the sample mean from each sample, and then this blue histogram is a histogram of the sample means. So this blue histogram is what's called the sampling distribution. It's not the population, it's not a value from the population, it's many values are drawn and a sample mean is calculated, and then those sample means are put into a histogram. So this is a histogram of sample means. Now what you can tell from this, and there's a few things we can tell, and we're going to call this result 1. Okay, first of all, if the population is normal, which is what we have here, it turns out the sampling distribution is also normal. Notice the mean of the population is 16, and the mean of the sampling distribution, the blue histogram, is about 16. Actually, if we did it more and more times, as many times as we could, that would become exactly equal. Notice the standard deviation, or the spread of this population, is greater than the spread of the sampling distribution. And actually there's an exact value. You can calculate the spread of the sampling distribution from the spread of the population. And these results are, I'm going back to my PowerPoint file, are on the next page on the PowerPoint, which says sampling distribution, this is result 1, for samples drawn from the normal population. The sampling distribution of the mean, which is again the histogram with sample means, is normal. The mean of the sampling distribution is equal to the mean of the population, and what we saw there, the population has a mean of 16. The sampling distribution also has a mean of 16. And the sampling distribution of the standard deviation of the sampling distribution, I said it was smaller than the standard deviation of the population. It's actually smaller by a factor of the square root of the sample size. So the standard deviation of the x bars, that's what this symbol means right here. The standard deviation of that histogram of x bars is equal to the standard deviation of the population divided by the square root of the sample size. Now, there's a second result that's equally important, because very often you don't know what your population is. Is it normal or is it not? We don't know. That's why we do the statistics, is to get information about the population. So rather than using a normal population, I'm going to use, say, something skewed. So there's a skewed population, something's not normal. Again, what I can do is I can draw a sample mean, and I'm going to make these, I want to make these samples a little bit bigger. 25 is the biggest I can do on here. So I'm going to select a sample of size 25. That's what's happening right now. Once that sample of size 25 is selected, the applet calculates the sample mean, and here is a sample mean from this sample of size 25. Now, as I did before, rather than waiting and doing this, it would take a long time if we did it one at a time. I'm going to collect 10,000 samples of size 25. Excuse me. And keep doing it more. There is 120,000 samples, all of size 25. From each sample, I calculated a sample mean, plotted those sample means in a histogram. And now, again, take a look. The mean of the population, in this case, is 8.08. The mean of the sampling distribution, the histogram of sample means, is also 8.08. Turns out they're equal. The spread of the spread or standard deviation of the population is 6.22. The spread of the standard of the sampling distribution is less than that. Again, we'll find out how much less. And then notice, even though the population was not normal, the sampling distribution, the histogram of sample means, is normal. And this is probably the most important result in statistics. If there is such a thing as a fundamental theorem of statistics, I think this would be it. And I'm going to call it just result 2, and here it is. Excuse me, let me get a drink. Called the central limit theorem. Says if for samples from a non-normal distribution, the sampling distribution of the mean, the blue histogram, is approximately normal if the samples are sufficiently large. And what we consider sufficiently large in statistics is anything greater than 30, greater than or equal to 30. 2, the mean of the sampling distribution, the blue histogram, is equal to the mean of the population. Again, same as result 1. And the standard deviation of the sampling distribution is equal, again, to the standard deviation of the population, which is here, divided by the square root of the sample size. When I say, as I will on the next in our class and on exams and quizzes, fully describe the sampling distribution of the mean, I want you to tell me its shape. And the shape, it's either going to be normal. I've never done a non-normal sampling distribution. It's either going to be normal because the population is normal, which would have to be given to you in the problem, or the sample size is sufficiently large. It's greater than or equal to 30. Tell me the mean of the sampling distribution, and tell me the standard deviation of the sampling distribution. So, fully describing the sampling distribution, I want 3 things: shape, the mean, and the standard deviation. Now, let's see how this is used. Okay, so using the sampling distribution. To use the sampling distribution, it's a normal distribution, so we can use it to calculate probabilities of basically sample means. What's the probability that the sample mean is greater than something or less than something? That's when you know you use it. When the question is not asking what's the probability of a single value from the population or the percent of the entire population, it's saying what is the chance that a sample mean drawn from that population is greater than or less than some value. To do so, you express the z-value of the sample mean by, as we did with the normal, take the sample mean minus the mean of the sample means, which we said is the mean of the population, divided by the standard deviation of the sample means, which is sigma over the square root of n. That gives me the z-score of the sample mean. Then, just as we did before with our normal problems, use the normal table or an applet, but we don't have access to applets in this course, to find the likelihood of obtaining the sample mean. And then eventually what we're going to do is going to use this information to make inferences about the population. So let's do one quick example. Quality control personnel regularly collect samples to determine whether factory machines are working properly. If the filling machine is working properly, for instance, the amount of soda in a 2-liter bottle is normally distributed with a mean of 2 liters and a standard deviation of 1 liter. Okay. I just realized something. Let's see. All right. Well, what I've done is I've switched from liters to ounces in my example. Sorry about that, but you'll get the idea. We've got so if the machine is working properly, the amount of soda in a 32-ounce bottle, which is the example I'm doing, is normally distributed with a mean of 32.2 ounces. Usually things are slightly overfilled, and a standard deviation of 0.3 ounces, and that will be in the problem below. During one production, a random sample of, say, 4 bottles is selected, and I'm going to have to adjust these questions because I've worked actually different, similar question, but I'll go through it when we get to the example. So here's example 1. Question A. What if I select a single bottle from that population? Remember, the population is normal. The amount of soda in a 32-ounce bottle is normally distributed with a mean of 32.2 and a standard deviation of 0.3. Now in your book that might say something like this, that the amount of soda, I'll call that S, is normally distributed with a mean of 32.2, standard deviation of 0.3. That's what you see in your book. So, what is the chance that if I randomly select the one bottle, that the amount of soda in that bottle is greater than 32 ounces? So the first thing you want to do, as we did with normal problems, is get a picture of it. 32.2 is the mean. I'm wondering what percent, or what is the chance that a single bottle drawn from the population, so there's no sample mean here, it's just a single bottle, is greater than 32 ounces. The first thing I need to do is find my z-score for 32. So that z-score equals the value itself, 32, minus the mean, 32.2, over the standard deviation, 0.3, and that actually equals negative 0.67. Go to your z-table. In your z-table, when you find a z-score of 0.67, that value, that probability is 0.2486. We want the percent, or we want the probability that a bottle has more than 32 ounces, so we have 0.2486 in this section. We want to get what's greater than the mean from this section, add those values together. So there's about a 75% chance, 74.86% chance, that a single bottle of soda drawn from this normal population contains more than 32 ounces. Okay, now the foreman of a bottling plant, this is what happens with quality control. Okay, wants to, again, foremen or quality control specialists will take samples. Okay, or in this case, it's a customer buying a sample. Boy, I have no idea what this problem is. It's a customer buying a carton, okay, of 4 bottles. What is the probability that the mean amount of the 4 bottles, so this is a sample of 4 drawn from that normal population, okay, what's the chance that that mean of the 4 bottles, that would be X bar, the mean of that sample, is greater than 32 ounces? To start that problem, and what I would generally do with this problem is I'd say, first of all, fully describe the sampling distribution of the mean for a sample size of 4. Okay, for a sample size of 4, well, first of all, we know that the amount of soda in all bottles, which we're going to call the population, and again, I want you to describe populations in words, is normally distributed. Okay, that's important because remember, there's 2 ways for the sampling distribution to be normal. Number 1, the population is normal, or number 2, if the sample size is greater than 30. In this case, the population is normal, so the sampling distribution is also normal. The mean of the sampling distribution is equal to the mean of the population, which we said was 32.2. The standard deviation of the sampling distribution, so that's what these 2 symbols are, the mean of the sampling distribution, the mean of the X bars, the standard deviation of the X bars, is the standard deviation of the population divided by the square root of the sample size. That is 0.3 divided by square root of 4, which is 0.15. Now, let's go to that problem itself. So a customer buys 4 bottles, a sample of size 4. What's the probability that the mean amount of the 4 bottles will be greater than 32 ounces? Again, I've got a picture down here. Try to always draw pictures. Here is the 32 ounces. Now keep in mind, this is not a single value. This is a sample mean. Let me get my pen out here. This is an X bar. That is a sample mean, the mean of 4 bottles. What's the chance that that X bar, this is a histogram of X bars, that the mean of those 4 bottles is greater than 32? Again, we need to find the z-score to use the z-table. So we say z equals the X bar, which is 32, minus the mean of the X bars, 32.2, over the standard deviation of the X bars, which we said in the previous page was 0.15. And when you do that math, that is negative 1.33. Okay, and again, the formula, which is an important formula, we're going to come up with this quite a bit. Z equals X bar, the X bar value, minus the mean of the X bars over the standard deviation, sigma of the X bars. Go to the Z table for a z-score of 1.33. We have a probability of 0.4082. We want the probability that we're going to be, or that the mean amount is greater than 32, so we want to add the 0.4482 with the 0.5, which is what's greater than the mean. Okay, and that gives us 0.9082. So there's about a 91% chance, 90.882%, that the mean amount of soda in the 4 bottles will exceed 32 ounces.